Okay, our goal now is to complete an instance declaration for our counter type for the monad class. We had been discovering our own bind function for counters and our own return function for counters. And in principle, this is enough to define a monad instance. But technically, this is a little bit complicated by the fact that we also have to define some other instances. So actually, let's look at the class structure with disregard to what methods we have to define first. Right? So we have the monad class, which defines bind and also return. And the superclass of the monad class is the applicative class. If we look at the applicative class next, we see that the applicative class has a number of methods that we still have to look at. And there is an old familiar method actually, which is called lift_a2, which is defined as part of the applicative class. And there is also a method called pure, which if you look at it, is looking extremely similar to return. And that's actually the reason why return is not part of the minimal definition of the monad class, because if we have pure already an applicative and pure serves the same purpose, then return can just be defined to be the same as pure. And then we have some other operators that we have not really looked at yet. Okay, but then in particular we see that applicative has yet again a superclass, and that is functor. And that one is familiar, but let's look at it again as well. And functor is a class that has no further superclasses, fortunately. And it essentially, so its minimal definition is to define this fmap operation, which we all know. Now, functor should not scare us, really, because at least in the context of maybe, we know that we can map over maybe types. And in the context of I/O, we have independently seen that, yes, we can map over I/O types. But in the counters example, we haven't seen this yet. But nevertheless, this gives us what we have to do, right? We have to give a definition for functor of counter, where we have to give a definition of fmap. That is the minimal definition here. We have to give a definition or an instance declaration of applicative for counter. And what was the minimal definition for applicative? Well, we have to definitely define pure. That's what the syntax says. And then we have to define either this star operator or lift_a2. And it does work with both of them, but let's go for this one in the end. It's just a choice. Okay. And I'm leaving these undefined for the time being. We're filling them in later. And then for the monad class, as we've seen, the definition is, the minimal definition is to have just bind. Okay, now there are two of these four functions that we have to define. So now actually there are no warnings, right? I mean, I have defined everything to be crashing, but this doesn't trigger warnings. So Haskell or GHC is happy in the background. I have been giving all the instances that I need. I have given implementations for all the functions, even though these implementations are all broken at the moment. So we do have to replace these four occurrences of undefined, but that's it, right? And two of them are actually easy for us to replace because we have already done the hard work. So in particular, we have defined bind. So we can use our fancy bind for counters in this position. It has exactly the right type, the type that is desired here, and that works. So I don't get any errors That's fine. And we have also defined return, and I said that pure in the applicative class is essentially serving the same role as return. So rather than using return as the return in the monad class, we can just use it as the definition for pure. And that works. And now we have two things left, fmap and star. And they're also easy, because we have already seen in the context of I/O that we can define fmap on I/O in terms of just return and bind. Right? We have even done this. So let me do this once again. I'll just call it fmap I/O, A to B to I/O A to I/O B. fmap I/O takes the function f. We use do notation, or well, perhaps if we want to be extremely precise, that we're really just using return and bind. Right? We can do it as this. We can take up this action here. Let's call it action, or let's call it computation. It's perhaps more general even. So we run this computation as a first argument of a bind. It has a result of type A, and then we said we are going to return f applied to A. Right? So this is only using return and bind. And we've already now seen that return and pure, they're equivalent. So equivalently, they're also just using pure and bind. And now if we have a version of fmap that is defined, that is known to be defined in this way, right, using return and bind or using pure and bind, then it actually works for any monad, for anything that is supposed to be a monad, for anything that defines return and bind. It does not just work for I/O, so we can actually call this function differently, and it actually is available in the libraries under the name liftm. Right? Not having a functor constraint, but having a monad constraint, because it is using bind, right, in its definition. But it only is using bind, and it is only using return or pure, and nothing else. In particular, it is not recursively somehow using fmap, and therefore it can be used as a definition of fmap if we already know that we're going to make our type an instance of the monad class. So we can put liftm here. And we don't even have to define liftm ourselves, because liftm is available in the module control monad. So as you can see here, this control monad liftm has exactly the same type as our liftm, modulo variable names, but it goes from some type A1 to R here to M of A1 to M of R. Strange choice of variable names, admittedly, but nevertheless, yes, for anything that is in the monad class. And additionally, we know, I mean, this is knowledge that we have to have, that this is not directly calling fmap. It is calling, it's defining this functionality in terms of return and bind, and nothing else. And that is why we can use this in this place. So we don't really have to do any extra work here. We just have to import control monad. And funnily enough, for the star operator, we can do something similar. So let's look at the type of the star operator again. So it is going to take an f, which in our case is counter, right? A counter of A to B to a counter of A to a counter of B. And again, the goal is to implement something of this just with return and bind and nothing else, or with pure and bind and nothing else. So let's try that. Let's try to write a function app that takes, if we have a monad M, takes an M of A to B and an M of A to an M of B. This is very similar to the type of function application, right? Function application, remember we had this dollar operator as some form of like giving a symbolic name to a function application. The function application operator takes a function of type A and B, A to B, and then takes an argument of type A and turns it into something of type B. We do the same thing here, only that everything is wrapped in an F. So we take something with a function result type and something with a suitable argument as a result type into something with a suitable result as a result type. Okay? So for example, we could take an IO action that returns a function and an IO action that returns a suitable argument and combine that into an IO action that returns the result. Or we could take a maybe with a function type and a maybe with an argument and a maybe with a result. And the idea is again that we are just sequencing these two components, get access to its two results, and then combine the two results by applying the function to the argument. So that is how we're going to implement app. Again, we could be using do notation, but if we want to be extremely precise, then we are just going to use bind and pure here. So we take something that is like a function, I'm still calling it f here, and we're taking something that is like an argument, so I'm calling it x here, and we're going to sequence in such a way that the function producing computation comes first, and we put it into a bind, and then we get a result out, which is exactly this a to b function. Let's call it a to b actually, right? According to the type that its result is. Then we next use this x computation, which results in an a. And then we have the two results, and we want to combine them by applying the a to b function to the a, getting a b, and then returning it, or using pure. It doesn't matter, pure and return are also going to be the same function, effectively. And now this definition of app is also short for apply, it type checks. And again, this is actually defined in control monad already under this name. So you can see that it has exactly the same type as our version of app that we have just been defining. So we don't actually need to do this ourselves. We can comment this out if we want to, and use the app function from the library, because again it is defined only in terms of return and bind. This is a little bit strange because we have this, like we have the super classes which are defined in terms of methods that are only using some of the methods available from the interface. So you have to convince yourself that you're not introducing some form of recursive dependency and a loop in this way, but it's actually fine, because we are giving as real inputs these two functions, and then app and liftm are defined just in terms of these two functions that we already give as inputs. It also seems a little bit strange, perhaps, if we can just get away so simply by defining fmap to be equal to liftm and star to be equal to app. Why have these classes at all? But the reason is simply that this easy option of defining the star operator and fmap in this way is the case in situations where we have all the three instances, where we have a type that is an instance of functor, applicative, and monad. Then we really only need these two functions as ingredients, one being bind and one being return or pure, however you want to call it. And you can define the other two in terms of them. But there are also types that are only an instance of functor but not an instance of applicative or monad. And then you have to define fmap yourself, and possibly a different way. And there are also some types that are only an instance of functor and applicative, but not an instance of monad. And then again, you have to define the star operator yourself in some other way, because you don't have bind available. So you cannot use liftm or app in order to define that. Right? But for counter, we have all three instances, and we don't really need to do any deep extra work. So we can relatively systematically give this class hierarchy by just filling the bind function in here, the return function in here, and then setting this one to app and this one to liftm. And then everything is fine. Everything type checks. And, oh well, actually, not everything type checks. I'm still getting name clashes elsewhere in the module. That is probably because I included control monad up here, and I had much further above, I had been defining other things like mapm or sequence, which are also defined in terms of which are also exported from control monad. So let's actually just say we only want liftm and app from the control monad module. Let's fix the problem in this way. Rather than getting everything that control monad has on offer, we are only interested in these two functions, and we are not importing all the rest. And then actually the module just compiles and loads perfectly. And we are now in a situation where we can go back to our label tree aux function, and we can replace return counter here with the normal return, and we can replace bind with the normal bind. And then we can reload, and we can call label tree again, and it still works. And now we can go even one step further and use do notation. We can use new L is the result of label tree aux of L. Lx is the result of step counter. New R is the result of label tree aux of R. And then the return in the end just remains the same. And this still loads. And this still works. So now we have made counter an instance of the monad class. We have do notation available, and we also have all the other functions available in principle that we have been using before. All the functions that are built just on the operations in the monad class. And as we've now seen, actually all the operations as well that are just built on the operations of the applicative class. And we have been glossing over that for a bit. So as you can see, the lift A2 operation that we have been using a couple of times to combine two actions together that we have been using for a while already in the context of I/O is actually only using operations from the applicative class. It doesn't really require bind. And that was also, if you remember, how we introduced things in the context of I/O. The big new thing about bind, and that is also the big difference conceptually between what the applicative interface gives you and the monad interface gives you. The big new thing was that subsequent computations can depend on the results of former computations. Whereas something like lift A2 is combining two computations, sequencing two computations and combining the results, but which computations you're sequencing is clear up front. They don't depend on the results of former actions. And actually, if you look closely in the label tree aux example here, right? If you look at these three operations, here we are not really using the full power of bind either, because we are running three computations, label tree aux on L, which gives us new L. We run step counter, which gives us LX. We run label tree aux on R, which gives us new R. But in these three computations, we're not using the results of the previous computations yet. The only place where we're using the results is this return clause in the very end, where we combine all the results. So the structure of the computations we're sequencing in the label tree aux example is completely clear up front, which means that we could rewrite this in terms of operations from the applicative class. Just not lift A2 because we have 3 computations there, but we would need something like lift A3. And that is something that we are briefly going to look at in the next video.